Alright, in this video, what I'd like to go over is a bit more on nucleophiles. So I kind of briefly talked about it in the last video. What I want to do is kind of talk about how can we take this a little further and identify, maybe go over some more examples of how to generate nucleophiles or how to kind of spot one, what is it once again about it that makes it nucleophile. So we won't go into as much, I'll try not to go into as much detail as I did before, and I'll put a link to refer you to the video if this is the first one that you're coming to kind of get a bit more detail. But if we look at this, we've talked about carbon in the last video. Whoops. We talked about oxygen, and then for now I'm going to write, let's say, sodium iodide, and we'll get into that one. Alright, so like we talked about before, to generate a nucleophile, what we want as a nucleophile is we want a set of lone pairs that are just sitting by themselves. They're not participating in a bond. For example, in this one we've got lone pairs here. They're just sitting there, and we can use them then to attack something. So if we look here, like we talked about before, let's do it on this first one, the base can come in, it can pull off that proton. So when we pull off that proton or hydrogen, then those electrons are going to go down there. And what that winds up giving us so those two electrons are going to go down there. We've talked about the fact that there now are 5 electrons around there instead of 4, so that carbon is negatively charged. And what that leaves us with is a hydrogen. Those 2 electrons there are going to be our bond, and now we've got that. So our nucleophilic portion now, there we've got a lone pair. It just so happens in this case that it's associated with the negative, so this is a nucleophile that's negative, and that can attack something. We've done the same thing. We don't need to do all of this again, but we've done the same thing with the oxygen. So we just push those 2 electrons down on there. That's going to give us our minus charge. And then if we had our base, we would get the same thing, our HB. And then that's going to be our nucleophilic site. So that's just kind of a rehashing of what we saw before. And obviously, this B would be right there, but I'm just not putting it in there for time's sake. All right. So what about sodium iodide? What does that look like? So we could think about, usually what we've seen so far in organic chemistry, we talk about bonds that have 2 electrons between them. So does that mean that sodium iodide is something like this? No. So what happens with all these organic molecules are what are known as covalent bonds. I'm pretty sure by this point in time you've heard all these terms, but if not, a covalent bond means that you're taking electrons and you're sharing them. So what's nice here is we can demonstrate that by drawing these 2 dots. In the last video I talked about, you can think about one electron being associated with one atom, the other electron being associated with the other atom, so you kind of have this equal sharing of electrons. That's going to be with atoms that are on the right-hand side of the periodic table. So, we've seen carbon and sulfur and all those. When you see one atom from the left-hand side of the periodic table and you see one atom from the right-hand side of the periodic table coming together, that's what's known as an ionic bond. So you do not get a sharing like this. This is not right. What it actually looks like is the atoms, as you're familiar with from general chemistry, the atoms on the left-hand side are going to be positively charged, and the atoms on the right-hand side are going to be negatively charged. So with the atoms on the right-hand side, what we've been seeing is we can actually draw all the electrons around it. So we know that iodine by itself wants to have 7 electrons in it because it's got the 7 on the periodic table. So it's like this. Well, what happens when you get sodium iodide? I'm just going to go over this very briefly. This is not really important. This is general chemistry, not organic. But what happens when you bring an atom from the left-hand side and the right-hand side together? There's a full electron exchange. So what happens is the sodium actually donates an electron. So let's just do this out since I've already started talking about it. What happens is sodium actually donates a full electron to that. So what happens is we talked about when you lose an electron, it's like losing a -1. So now sodium is positively charged. We're donating that electron on the iodine, and this is the one we're actually going to draw out. So that's going to be 1, 2, 3, 4, 5, 6, and now we have a total of 8. For iodine to be neutral, it wants 7. It has 1 electron that's extra. So that's going to be a minus. Why did I go into all of this? Because this is general chemistry. What this demonstrates is you can have a nucleophile that's not an organic molecule like a carbon-carbon bond or an oxygen-carbon bond. You can actually have just an element that you see on the right-hand side that's by itself. The ones that you're going to see are going to be essentially the halogens. So you're going to see I minus, Br minus. These can actually act as nucleophiles and sometimes bases. So that's what I wanted to show you in this specifically, is that you can actually generate a nucleophile from a halogen. So let's go into a bit more detail. Now that we've seen all the electrons, just lost my train of thought here, what I was going to do. Oh, so let me elaborate a bit more, and let's talk about, so we've seen a carbon-hydrogen or oxygen-hydrogen bond. Can we have a carbon-carbon bond that actually can turn into, let's do this, let's do R. Can we actually have a carbon-carbon bond itself that can turn into a nucleophile, something that can come in, so we'll just put X, something can come in and grab that off? No. So what you've seen so far is it's important in order to generate a negative charge on a carbon or a hydrogen, a carbon or oxygen with single bonds, is it has to have a hydrogen on it that you're pulling off. However, when we get into double bonds, so let's say we have a carbon-carbon double bond, something like this. Like I've talked about, every single bond is an electron. It has 2 electrons. So if we think about this double bond, we can kind of recontextualize this. And now if we think about our double bond, what if we thought about it in terms of 2 electrons? So what we're really talking about is that carbon has 1 electron and that carbon has 1 electron. Now what I always thought, there was one day I sat down and I thought about this, and I always thought it was cool, but that's just me being a nerd because I like chemistry, is you can start to push these around and think about these in different ways. So what if we took both of these electrons and we took both of them and we just started pushing them on different atoms? So instead of saying one's on one carbon, one's on the other, what if we took both of the electrons and we pushed them on that carbon? So we took them and we brought them up there like that. If we think about what we've been talking about before, if we put 2 electrons on a specific atom and they're not associated, they're not kind of one's on one atom, one's on the other, but now they're both there, that actually creates a full negative charge. And what that's going to do here is when we pull electron away from that, that's going to generate a positive charge. Now why is that? If we kind of break this apart, so I'm going to put this up here, I'm going to shrink it, we'll go into a little bit of detail. So let's say that's a carbon there in the middle, and then I'll try to do it at the same angle, and that's going to be a carbon there, and that's going to be a carbon there. Now obviously we know there's associated, I should have done it this way, carbon, carbon, and then I'll draw everything out just so we can see it. So that obviously has understood 3 hydrogens. That was a double bond, so now this is going to be, whoops, that should, yeah. The double bond is on this side, so that's going to be H, H, and then I'm going to draw our second double bond there. So you can see that if we take both of those well, let's just go over this. So if we look at this carbon, we have a total of 4 electrons around it, so it's neutral. With our double bond, we have a total of 1 from that. And then with double bonds, I guess I never went over this, if we have a carbon-carbon double bond like that, it would look like that with dots. Forgot I never actually went over this. So in terms of counting atoms, we know or electrons, we know we still want 4 electrons around each atom. When we get into double bonds, we've only talked about single bonds. You still look at 1 electron from each bond is associated with the atom. What I mean by that is if we look at the carbon, we have 1 electron, and then we take 1 from each of the double bonds. So we still have 4 around it. And then we look at the other side, we have 1, 2, 3, 4. So that's why that's neutral. So now if we go down here to this one, we've always just proven that. This obviously still has hydrogen on it. So that would be 1, 2, 3, 4. So we have 4 around it. What happens when we do this green arrow up here and we push those electrons? What we're doing is we're taking both of those electrons, and I'll do them in red, and we're dumping them specifically on that carbon atom right there. Now you can see this is getting really messy, so I'm going to make this a bit easier, and I'm going to eliminate that, and I'm going to eliminate that so we can look at just the central carbon atom. And what we'll do is we'll put it in green, it's green, and green. So now we can see by dumping those 2 electrons on there, and I guess I should have left this one. By dumping those 2 electrons on there, now we can see we have a total of 1, 2, 3, 4, 5. We have 5 electrons around there. So that's going to give us a minus charge. But what we've done is when we've taken both of those electrons away, now we only have 1, 2, 3 around there, so we're missing one. So that's going to be a plus. I realize that got a bit messy, but hopefully that kind of conveyed. So let's just go back to this one. If you've looked at the other videos, this one should make a bit more sense. But what we've done is we pulled those two electrons. So now we've got a minus and a plus. What's significant about this? It shows you that a double bond at any given time has a plus and a minus on two different carbons. We don't have to go in that direction if we wanted to. What if we pulled the two electrons in this direction? So we do the same thing. We pull both electrons over. So what that's going to do is give us our two electrons there. So now that's going to be a minus, and that's going to be a plus. So now you can see that at any given time we can think about this double bond as having a plus either on if we look at this one, the more substituted carbon, or we can have the plus on the less substituted, but there's always a plus and a minus. And now we can see that double bonds are nucleophilic as well as electrophilic. So I'll go into this a bit more once we start doing mechanisms to show you that just knowing this simple fact right here, it makes it so much easier to do chemistry when you start thinking about alkenes and figuring out why you get a Markovnikov, why you get an anti-Markovnikov just by looking at this. But this was just to demonstrate that you don't need a carbon-hydrogen bond to turn into a nucleophile. You don't need an oxygen-hydrogen single bond to turn into a nucleophile. You can actually use existing multiple bonds. You can also think of triple bonds as well, if they can be converted into nucleophiles.